From Maryland. So, so this is Alexey Goshkov, who will be talking about Rydberg interactions.
Thank you, Anders. Like Mohammed, I also started my PhD by working a little bit with Anders, so I guess there's some correlations here. So thank you very much to the organizers for the invitation, and thanks for you for being here. You know, in this horrible weather and the last day of the conference. It's thanks again. So before I begin, let me advertise a new quantum center. It's a quantum information theory center, QUICS, that we've recently launched at the University of Maryland, which is a different center from the JQI. And both the JQI and QUICS offer annual postdoctoral and graduate fellowships, and there are also postdoctoral positions in my group. So well, please apply. So I will talk today about a few body and many body physics with Rydberg polaritons, something that we've heard already a little bit about in this conference. So this doesn't really require repetition, but I'll just briefly say it for those who are maybe here for the first day. I don't know, maybe there are none of you like this. So photon-photon interactions at few photon level, have many applications. That's why most of us are here. They can be used to build better quantum networks, to do perhaps better optical quantum computing, or even maybe non-optical quantum computing by using these photons as interconnects between separated modules. They can also be used to generate non-classical states of light that can perhaps be used for better metrology. And finally, these strong photon-photon interactions can be used to study exotic few-body and many-body phenomena, as exotic as the things that Mohammed just talked about, for example. And this will also be the focus of this talk, so studying these exotic few-body and many-body phenomena with strongly interacting photons. So a typical approach to interactions between optical photons involves coupling these photons to a nonlinearity that's using the nonlinearity induced by individual or non-interacting atoms. And this was indeed the topic of the discussion in the beginning of the conference, where microwave photons were coupled to individual solid-state qubits. But then later in the conference, we also moved to another approach, which also some people have talked about, is the use of atom-atom interactions as opposed to individual atoms to induce interactions between photons. So the cartoon picture here is like this. You imagine two photons and two atoms. And then in our case, we will use the Rydberg states of these atoms to couple the atoms together. And then we will use EIT, or electromagnetically induced transparency, to couple atoms to photons, and then you see that this effectively creates interactions between the photons. This will be our approach. And to describe this approach, let me first review Rydberg states and EIT. Before I do this, let me point out that because of its promise to achieve these strong photon-photon interactions, quantum optics in Rydberg EIT media has recently attracted a great deal of experimental and theoretical attention. And indeed, we've already heard talks by Thomas and Anders, and we will also hear Sebastian and Vladen talking later today about this topic. Indeed, the interactions at the level of single photons have already been demonstrated experimentally. And so this talk will be about trying to describe the propagation of quantized light in these strongly interacting Rydberg EIT media outside of the perturbative regime. So the two ingredients again are Rydberg states and EIT. So although I know that Thomas has reviewed it and other people have reviewed it, let me just also review it in case you forgot overnight. Rydberg states of atoms are electronic states with a principal quantum number n that's much larger than 1. So this is a cartoon for a ground state atom, where the outer electron is orbiting a core. Then this would be the cartoon of a Rydberg atom, where the electron is in a much larger orbital. As a result, these Rydberg atoms have very large electric dipole moments, which in second order perturbation theory give you these very strong van der Waals type interactions that become stronger and stronger with a larger principal quantum number with this huge power of 11. So you can get these very strong interactions between Rydberg atoms, and interactions allow us to study sort of more exotic physics. Now let me review electromagnetically induced transparency, which we will use to couple our atoms to our photons. Imagine an ensemble of two-level atoms made up of ground state G and excited state E prepared in the ground state. And then because of this spontaneous emission gamma, if we consider a single photon that's resonant with this two-level transition, the single photon will normally be scattered by this ensemble. And the output intensity will be exponentially suppressed relative to the input intensity with the optical depth in the exponent here. That's the definition of optical depth. However, if we have another stable state R that is coupled to the excited state with a classical control field, this extra field can actually suppress the scattering of the single photon. So the single photon can actually happily go through now. The reason this happens, as already has been discussed, for example, by Effie, but by Thomas, and by probably several other people, is that these photons form dark state polaritons, coupled atom-photon excitations, where here E dagger of Z creates a photon at position Z, R dagger of Z creates an R excitation at position Z, G here is a collectively enhanced atom-photon coupling, and omega, is this Rabi frequency. In typical experiments, G is actually much larger than omega, so these dark state polaritons are dominated by the atomic part of the polariton. And as a result, because it's the photonic part that gives rise to propagation and it's dominated by the atomic part, well, they don't move very fast. So they travel at a reduced group velocity Vg. And this results in this pulse compression. So in fact, an entire pulse can often be compressed inside the medium. And this, we like this, so we can then have them interact with each other and do interesting physics. So now let's consider changing the two-photon detuning here, or equivalently the frequency of this incoming probe single photon. Then we will see that when the two-photon detuning is 0, we get full transmission. That's what we just discussed. But if you imagine varying this two-photon detuning, you will see that very quickly the transmission will drop to 0 outside of some so-called EIT transparency window, which has a bandwidth omega EIT that we will use later. So let me now outline how we will use these Rydberg EIT media. We will first show how to use them for dissipative interactions between photons, where we will show how these dissipative interactions can be used to generate single photons or trains of single photons. And then we will use these Rydberg EIT media to generate unitary interactions between photons, which can be attractive or repulsive. We will show how to get shallow or deep two-photon bound states. And finally, exotic two-photon bound states that I will call Coulomb bound states. So let me start with the dissipative interactions between photons. Suppose we have two photons incident upon our three-level medium. Now this R state before it didn't really matter in the earlier slide because there was just one of those states. So now let's assume that this state R is a Rydberg state, so they will be interacting strongly with each other. And let's suppose the first photon is propagating at position Z1 and the second photon is propagating at position Z2. It's a cartoon picture. In order to form a dark state polariton, the first photon excites the atom at position Z2 to the Rydberg state R. This Rydberg state now results in a shift of the Rydberg state at position Z2 by the distance-dependent shift, V of Z1 minus Z2. That's the Rydberg-Rydberg interaction. And then if this interaction, this shift is sufficiently large, then the second photon will effectively see only a two-level medium, The reason is, the shift is so large that the control field has nothing to couple to. And the second, and this means that within some radius that we will call the Bloch radius, this interaction is so large that the second photon will just get scattered. And so two photons cannot propagate without losses if they are sufficiently close, if they're closer than this Bloch radius. So this was demonstrated in an experiment, which I believe Vladen will describe perhaps in a more detail than in this one slide, which I will use to motivate the remaining theory. So in the experiment, a continuous wave coherent input was incident upon the medium. And then the question is, what comes out on the other side? From the previous slide, we know that two photons do not like propagating next to each other because of these Rydberg interactions. And indeed, photon anti-bunching was observed in the output. And in the case of really weak input, the experimental results perfectly agreed with a two-photon theory because we didn't need to go beyond that. However, for high intensity, the theory is actually hard. And it's hard because it's really a strongly interacting, time-dependent many-body problem, and one might expect it to be hard. So in the remainder of this dissipative section, I will present some steps towards a theory for arbitrary input intensity for solving this time-dependent many-body problem. And in the process, I will show that the system can be used to generate single photons or trains of single photons, which one may or may not call crystals. So let's first assume that we have an n-photon Fock state that's incident upon our medium. And let's suppose that the length of the medium is equal to the Bloch radius, so the entire medium is blockaded. And let's suppose that our EIT is set up in such a way that after EIT compression, the pulse completely fits inside the medium. Furthermore, let's assume that the single photon EIT is perfect. So no matter how narrow our pulse is or how wide it is in frequency space, suppose that the single photon always goes through. Then it means that the first photon out of these n photons, the first photon will always go through. But now, because this single photon completely blockades the entire medium by creating this polariton, all the remaining photons get scattered. So it means that at the output, we will get exactly one photon out of this n-photon Fock state. However, this one photon will be impure in the sense that I will explain in a second, and will also be shorter than the original mode that's coming in. So Offer Fürstenberg coined this term sick, which I think picked up a little bit. So this photon will be sick in some sense. So by impure, I mean the following. So here's an example of an impure photon. It's a photon that's in a mixture, in a classical mixture of two different spatial modes. So this is an example of an impure photon. That's not quite what we're going to get, but something like this. So why is this taking place? Well, imagine, this mode is propagating and it's partway into the medium, and then we get a scattering event. So the scattering event means that there must already be a polariton inside the medium that caused that scattering event. So this scattering event that projects this first photon onto some sort of shape inside the medium. So this, on the other hand, means that because we're not really detecting these scattered photons, depending on when the scattering takes place, the projection happens on a different type of wave function, and this gives rise precisely to this impurity. At the same time, you also see that this wave packet is shorter than the original mode because it's been projected on a piece of it. And if you increase the intensity, the n here in this n-photon Fock state, the larger n is this first scattering event will happen earlier and earlier, and it will give rise to a shorter and a shorter photon, and it'll be more and more sick. So why are shorter photons more sick? Well, because a more intense shorter photons will have a larger bandwidth, and they will be harder to fit inside our EIT medium. And therefore, they'll get scattered and they will die, and, because they're sick, so that they die. So this was an n-photon Fock state, but similarly, if you have a coherent input, and if it's sufficiently intense that the probability of vacuum vanishes, then it immediately gives you a deterministic but impure single photon source, under the assumptions of very good EIT. Okay, so this was a single photon. So now let's suppose we have, again, intense coherent input. Again, let's suppose the length of the medium is equal to the blockade radius. But now, as in contrast to the previous slide, let's assume that this pulse is really long, such that it actually does not completely fit inside the medium. So then, the pulse moves in a little bit, and at some point we get a scattering event. So then, like in the previous slide, this means that there must be a polariton already inside the medium that caused the scattering event. So then things propagate a little more. Then this guy, while it's still inside the medium, it blockades the full medium, because our medium has a length equal to the blockade radius. And so everybody that arrives, all the photons that arrive while this guy is inside the medium, they all get scattered. Eventually, though, it moves outside the medium, and now there is space for another polariton to go in, and then it goes in. And then another scattering event projects the second polariton on its really short wave packet. Things propagate, more photons scatter, a third one gets in, and the process goes like this, such that at the end, in the output, we get a train of photons, in principle, that are just spaced, in space here, they were spaced by the blockade radius, which is the length of this medium, and at the output, they're just spaced in time by the blockade radius divided by the group velocity of the polaritons inside the medium. So again, at the output, we have basically our previous slide, which is the single photon source, but it just repeated every RB over VG. So it's a train of short single photons, and depending on your preference, you may or may not call this a crystal. So the more intense the input is, the more precise will be the spacing between these photons, because if the if the input is really weak, we'll just have the scattering event occurring once in a while. So these guys, these polaritons, will not really be so nicely projected into their desired positions. But if the intensity is really high, then as soon as one polariton goes in and gets projected, then it moves through. Then the next one gets projected, and we get these short photons that are precisely spaced by RB over VG in the limit of large input intensity. However, these shorter photons, the ones that form this nice crystal, they also need a better electromagnetically induced transparency, and this cannot be infinitely good. So there is some sort of a balance, and this balance can be achieved if our blockaded optical depth, which is the optical depth of this entire medium, is much larger than 1. And I will discuss this in the next few slides. So the approach that we will take is we will assume that we will separate our entire problem into two, and it's an approximation. We will first assume that this entire process happens with perfect single photon EIT. In other words, we will assume that no matter how sick the photons get, they will, as long as it's a single photon, it always goes through. So it's like a limit of perfect EIT. And then after we get our train of sick single photons, we will EIT filter them. So that's an approximation that we hope is good in the limit of good EIT. So again, the idea is that we will first assume that our medium has perfect single photon EIT with Rydberg interactions, and we get this train. And then we will send this train just through a simple linear EIT filter that will filter out all high frequencies. And then maybe if these photons are too short in time and too wide in frequency, then maybe one or more of these photons will get scattered. So this picture sort of emphasizes the interesting, well, perhaps obvious, sort of this particle-wave duality of these Rydberg polaritons. So on the one hand, in this picture, these Rydberg polaritons behave sort of like hard spheres because they really don't want to stay closer to each other than this RB over VG, and they kick out everybody who is sitting in the wrong place. But at the same time, to get through this EAT filter, these photons need to be sufficiently wide in frequency space, and really we need to be thinking of these photons as waves. So let me first focus on this problem, and then at the end I will just explain how this EAT filtering works and what it does to our train of photons. So to understand a little bit better what happens in this process, let's suppose we have a square pulse coherent state that's coming in, and it moves a little bit into the medium. Then again, a scattering event occurs, which says that there must be a polariton inside the medium that caused that scattering event. And let's color code this as green. So the scattering event tells us that the first polariton is already inside the medium. Then this polariton propagates a little bit and starts coming out. So now something that could not happen before in a single photon source is by the time the polariton starts coming out in that single photon source, there was nothing else that was coming in. But now there are photons that are coming in even when this guy is coming out. So if a scattering event occurs right now, the scattering event tells us that the first polariton, this guy, must still be inside the medium to cause that scattering. So this does yet another projection, in fact. So this guy gets shortened not only as it comes in, but also as it comes out. So it's really, being sickened by these scattering events. Now, equivalently, the scattering event might mean that the first polariton has already exited, but the second one has already come in, sort of like a picture like this. And one needs to take into account both of these processes. But eventually, the second one does come in, and then the third one comes in, and this process repeats. So that's roughly what's going on. So now let's be a little bit more precise and want to characterize the train of photons that comes out, because we will need to stick it through the AT filter. Let's suppose that this square pulse coherent state has average photon rate R. So then at the output we get this train. Let's suppose we look for the first n photons in this train, and let's number them from 1 to n. They'll be spaced by RB over VG. And by the arguments that I just presented, it seems pretty natural that the higher this rate is, the more and the faster these projections takes place, and the shorter are these photons. So in fact, the durations of these photons are just 1 over the rate of the incoming photons. But it turns out that later photons are a little bit longer, and the nth photon is in fact as duration square root of n divided by the rate. So the reason this lengthening is happening is because, in some sense, these later photons are sort of forget the initial condition. So the initial condition is that at time equal to 0, the first photon comes in. But then because our rate is not infinite, some long time after this, we're not exactly sure, whether this nth photon is right here or maybe there, and this is why this gets wider and wider. The bandwidth of this photon is pretty much Fourier transform limited, so the bandwidth is just R. But the bandwidth of this guy, it doesn't get shorter. There's just an uncertainty of where it is, so it's impure, but the bandwidth is in fact still R. It's not R over root n. So then we have the following conditions for making a crystal. First of all, we want to make sure that the width of this last nth photon is shorter than the spacing between the photons, otherwise it's not a very nice crystal. And second, we want to make sure that none of these photons get lost when we send them through our EAT filter. So if P loss is the probability of losing one of these photons in the EAT filter, we want to make sure that n times that is less than 1. So the probability of loss is just given by the bandwidth of one of these photons divided by the width of the EIT transparency window. the width of the AT transparency window is just the Vg times the square root of the optical depth divided by the Bloch-A radius. And now, this condition gets easier and easier to satisfy the larger our rate is, because the shorter these photons get, while this condition becomes harder and harder to satisfy the larger the rate is. And it makes sense, there's this optimum that we need to reach. So the optimum takes place when actually both of these conditions are equality, or roughly equality. And then I can even walk you through this very simple math. So let's make this condition equality. And also let's make this condition equality. So I have this n times r, rb over vg, and I just put square root of optical depth on the other side. So now we can plug in this expression in here, and now we have n to the power 3/2 is equal to ODB to the 1/2. So this shows that n scales as the cube root of the blockaded optical depth, which is indeed the full optical depth of our medium, because we assume the medium has optical depth duration equal to the Bloch-A radius. So is this really the best we can do? Because this scaling is not very good. So it means that if I want to get, say, a train of 10 photons, I will need a blockaded optical depth of 1,000. And that's pretty crazy, right, Sebastian? Yeah. So can we do better? Well, it turns out this, square root of n scaling here is not necessary. I mean, in principle, if I'm clever, I might be able to just get every photon have duration 1 over r and bandwidth r. And then really I won't be able to do better than this. And indeed, I can get rid of this square root of n. If it were 1 over r, then this condition will soften, and the number of photons in our train will become a square root of the optical depth, which is a little bit better. So now maybe you need 100 blockaded optical depth to get 10 photons. And indeed, we can achieve this by using either a pulsed control or a pulsed probe. While in the discussion so far, everything was a continuous wave. But I won't go into those details. Okay, so in the remaining 10 minutes, or 9 maybe, let me move to unitary interactions between the photons, and I will discuss how to get attraction and repulsion between the photons, how to get shallow and deep bound states, and also how to get these exotic Coulomb bound states of 2 photons. So now we assume we're off resonance. Delta is much larger than gamma. And again, we have 2 photons propagating to position Z1 and Z2. To form our Rydberg polariton at position Z1, the first photon excites a Rydberg atom. This shifts the Rydberg atom at position Z2. And then if these 2 photons are too close, the shift is really large, that the second photon will effectively see now an off-resonant 2-level medium, and instead of getting scattered, it will acquire a phase. So this off-resonant experiment has also been done, and perhaps Vladimir will talk more about it. So the second photon, as we just discussed, will imprint a phase, the 2 photons will imprint a phase on each other if they're sufficiently close. So now I need to introduce one more concept here. Let's suppose we can choose this 2-photon detuning delta, and then we plot here the imaginary and real parts of the susceptibility. And then we can, so here at 0, this is precisely where the imaginary part vanishes. That's where we get perfect transmission. And we also have here this curvature of the real part of the susceptibility. And indeed, this curvature gives rise to a mass of a photon in any Rydberg medium. So we weren't the first ones to discover this. There were papers from a long time ago by Michael Fleischauer and perhaps by others. So we have these photons with a mass, but we also have a refractive index or imprinted phase that depends on photon-photon separation. Well, this gives rise to a potential well in relative coordinate between the 2 photons, which can in turn be interpreted as an attractive force, and which in turn might give rise to a 2-photon bound state whose evidence was observed in this paper. So how do we describe this in more detail? Well, we assume the following 2-photon wave function, where psi of Z1 and Z2 is the amplitude of having 1 photon at position Z1 and 1 photon at position Z2, while here we have the parts of the wave function that have one or both excitations in the atoms as opposed to the photons. Let r be the center of mass of the two photons. Little r be the relative coordinate between the two photons. In a homogeneous medium, the center of mass momentum k will be a good quantum number. So this is just the Fourier transform with respect to the center of mass coordinate. And let's finally assume that the detuning is much larger than gamma. And then you can just exactly rewrite the evolution equation for all of these different amplitudes in terms of the single component massive Schrodinger equation. So the time-independent Schrodinger equation with energy omega for this wave function will reduce to a single component massive Schrodinger equation where all of these things here will depend on the center of mass momentum k and the energy omega. And this equation can describe a lot of interesting physics. So in particular, for a red detuned control, where this delta here is greater than 0, and omega is less than delta, we can get attraction. So at large separations, we have van der Waals type interactions, while at short separations, it saturates. And we can have either, we can have bound states here. For weak interactions, we can have one bound state. For strong interactions, we can have many deep bound states. If omega is larger than delta, it turns out the potential flips and we get a repulsion. And then one can, in principle, imagine using this repulsion to crystallize photons. So in the remaining 4 minutes, let me discuss this idea of Coulomb bound states. So now let's suppose that instead of having a red detuned control field, we have a blue detuned control field. Turns out we can get exactly the same equation, but now this potential will be different. And to motivate what it looks like, let's assume that the Rabi frequency is much smaller than the detuning. And then if we consider the dressing of states E and R with this control field, we have here an omega squared over delta shifted dress state, which gives rise to Raman resonance. So in particular, if you consider changing the two-photon detuning, you will see that when this little delta is equal to omega squared over delta, then you actually hit this Raman resonance, and you move from this EIT, which has no absorption, to this huge absorption at omega squared over delta. And indeed, this huge absorption has been used before in the context of Rydberg EIT to do, for example, photon subtractors. But if instead of tuning this two-photon detuning, if we instead consider bringing another Rydberg atom towards this guy, then as they come closer and closer, the state will just shift because of interactions, and it will also go through this very same resonance. So as two atoms come closer to each other, they again go through this resonance. So this means that now our interaction, instead of being a nice dip, it has this resonant feature at the blockade radius. And if you expand the interaction around R equal to RB, you will find that it actually has a Coulomb-like behavior, so 1 over R minus RB. So photons interact through this Coulomb-like potential, and we can have bound states. We can have this deep one, and then shallower and shallower bound states. So the spectrum of these bound states will have this characteristic minus 1 over n squared spectrum of the hydrogen atom. And if we go to higher enough n, it seems like we might actually be able to get a Rydberg bound states of 2 Rydberg polaritons. At the same time, these photons are bound a finite distance apart from each other. They're bound the blockade radius away from each other. So they look like a molecule with a non-zero bond length, which is very similar to what James discussed yesterday. And we hope to use these guys to build more complex states. Now, since I'm really out of time, let me perhaps, well, I'll briefly describe this. So this is a movie where I plot the absolute value of the two-photon wave function, which is very similar to the movie you've seen in James' talk. And these are the two lines where the two photons are exactly the blockade radius away from each other, which is where our Coulomb state is prepared. And then we just let it evolve, and we see that it actually, I mean, amazingly, it moves backwards in the negative z direction. So again, it moves backwards. So we see negative group velocity. Turns out if you change the principal quantum number of these bound states, the group velocity will also have this characteristic -1/n² feature. So this is a nice way for detecting them. And also, you see that these photons, as they propagate backwards, they also decay. And this is actually a good thing, because we only have rightward propagating modes. And if we have rightward propagating modes, it's impossible to have a true bound state that propagates in the opposite direction. So it means that they're not really fully stable. It means that they are, in fact, metastable. And I don't really have time to discuss why they're metastable. Well, it turns out that as they propagate, they decay into something we call a continuum of Rydberg molecules, where two Rydberg atoms are just bound some distance away from each other and really decoupled from all the light. So they decay into these Rydberg molecules. So I'll skip these slides. These are the Rydberg molecules. So I discussed the dissipative interaction between photons, which give rise to single photons and trains of single photons. Unitary interactions give rise to attraction, repulsion, shallow and deep bound states, but also these exotic Coulomb bound states that move backwards and decay into these continuum of Rydberg molecules. So there are lots of things that one can study. So this field is quite exciting. In particular, Yidan Wang, who is here in the audience, a student in my group, so she's working with a lot of other people, including the Harvard-MIT experimental group, on three-body physics of these Rydberg polaritons. Let me thank my collaborators, which is the entire Harvard-MIT experiment, which has grown since then, but I'm listing only those people who've contributed to the stuff that I mentioned. The work on Coulomb states was led by Mohammed Maghrebi and Michael Gullin, so it was an equal contribution. And then the work on these photon trains was really headed by Emil Zuthen, who is a student of Anders Sorensen, and I'm still trying to convince Anders to join us in this effort, and I think I might have succeeded. Well, I'm not going to go through this. There's some other related work on topological matter and AMO systems, and I will also advertise the paper that Mohammed advertised, but I will also not talk about it. Laughlin states with Rydberg polaritons. We also have very related work on dynamics in long-range interacting quantum systems, including 1D systems, and we've talked about these long-range interacting systems for the entire workshop. You can study some causal regions, so I will not talk about this either. A student in my group, Zach Eldridge, who is also here in collaboration with Derek Chang, we're working on a self-organization along chiral 1D waveguides, and I think we'll hear about this in Helmut's talk. Hopefully, we'll still have something left to do after the talk. I don't know. We're also working on a non-equilibrium many-body steady states using Keldysh formalism, and this is left by Mohammed Maghrebi because all of these photonic systems, they're very much dissipative and driven, so you can study this. Well, thank you for your attention.
Yes, other questions?
You said this movie is two photon bound state. Is that how do you initialize that state?
Yeah, so we literally we solve theoretically or numerically, we just solve for our bound state. Well, as I said, it's not quite the true bound state because the true bound state will not be decaying. So we solve for that thing that we think is a bound state. Then we initialize it, and we see that it moves backwards and decays. But we can also solve for the full, in principle, for the full bound state that will have a superposition kind of this thing plus these Rydberg molecules, and then that thing actually will not decay, and it will also not move backwards.
I guess more what I meant was how in experiments.
Experimentally, right? Yeah, right. So experimentally, so again, I didn't want to go into details. So in the paper we have a protocol. So the protocol first involves storing a say, a weak coherent state, or maybe if you have two photons, the two photon Fock state, you store it using usual lambda EIT onto some stable state. Then we'll need to imprint some center of mass momentum onto it, maybe by applying a magnetic field gradient to get the right k vector needed for this bound state. And then we map it up to the Rydberg state, and perhaps we need to do it with a very clever control field just to make sure we excite just the right part of the wave packet. And then we'll let it go.
Just referring to the first talk, I mean, you get this first part, you get these scattered photons, but some of them might eventually go out in the forward direction as well. And as far as I remember, the higher the density is, the more the probability of forward scattering. So if you have too big optical density, a lot of your photons which you draw going out the side will come out forward. I don't know if this is a problem.
Well, not for these, not for these spontaneously scattered photons. As long as they come one after the other, as long as they like don't come all together and like amplify each other, then there's no enhanced probability of going forward. They just spontaneously scatter into 4 pi, and we ignore that.
Only for point scattering, you have this collection of
No,
scattering.
no. The first photon spontaneously scatters into 4 pi always. There's no enhancement
No,
forward.
because you will, okay, we can discuss this later.
Okay.
So kind of somewhat related question. On the cross, about the cross part of the talk.
Yeah.
What's kind of the fundamental signature of this?
Wow.
And secondly,
Yeah.
Secondly, can these things exist in steady state?
So, so the experimental signature is, the thing that we've been looking for the past 3 years is these dips, multiple dips in G2, but we're not seeing that. That would be the experimental signature.
So these are steady state.
I mean, it's sort of. It is sort of the steady state version. It will just like once in a while, this thing will just sort of lose its. It will lose its sort of ordering, I believe.
It will be a defect basically, and then it will
yeah, I think so. That's what I think, right? But we can talk about it more. I mean, we also have a prediction for how the intensity of the outgoing light will change with the incoming intensity. And the prediction is that it will not saturate; it will just drop to 0, which sort of contradicts, figure 3a, if you know what I'm talking about. We observed experimentally, but.
Last question.
Yeah, I guess I had kind of a related question. As these photons are getting broader in this chain, right? If I look at, say, the nth one, which is pretty broad, and the one after that, this one is pretty broad with respect to the time of the first photon. But if I look at just those two, n and n plus 1, do they again have a tight correlation with each other, as if I was looking at the first?
Yes, exactly. That sort of answers right, exactly, partially Misha's question, right?
Last one.
I'm assuming that the whole medium is dislocate
Yes.
for these predictions.
Yes.
So I think that might change things, right?
Yes. The reason we assume that the medium is equal to the Bloch radius is because anything that goes past this, it will just make our EIT filter more severe, so it doesn't help us. It'll probably kill things even more. But.
All right, let's thank Alexey once again.